Hello everyone, my name is Asta Kachi and I am going to be talking to you about embedding extraction and speaker identification workflow using NVIDIA NeMo toolkit. NeMo is basically a neural network based toolkit for building and deploying conversational AI models. It provides wide range of pre-trained modules. However, in this presentation, I will be walking through the steps involved in the speaker identification task using NVIDIA NeMo Titanet large model. Speaker identification task involves various steps such as speaker embedding extraction, clustering, and speaker identification task. To understand this methodology, let me walk through this code. For this task, we will be using Google Colab Notebook as it provides the required resources. Here I have first connected my Google Drive and as it takes a heavy time for installing the required libraries for the NeMo toolkit, I have already uh, done those required steps earlier. Similarly, here we are importing the necessary libraries which are required. To extract speaker embeddings, that is the first and that is the important part of any speaker identification task, we need to create the speaker manifest file which contains wave file, duration and dummy speaker label. So as we see here, we create the manifest identification file and the required dictionaries and the variables are been given here like audio file path, duration, label and are those appended to the JSON dumps here. Next step is to create the speaker embedding file. NVIDIA NeMo Titanet uses a large number of features to extract speaker embeddings. Some of them are 1D depth, noise separable convolutions, squeeze and separable layers, channel attention based statistics, linear layer, I vector and X vectors. This all consist of various DNN architectures. Specifically talking about the Titanet network, which creates the speaker embeddings, uses a transformer based encoder and decoder architecture. There are n number of encoder modules where each encoder module consists of 1D depth wise convolution layer and pointwise convolution layer, followed by batch normalization. Again, that is followed by the ReLU and the dropout function. This whole layer or this whole process is then repeated R times. And finally, we get the and finally all those are passed through the squeeze and separate layer. And after getting the encoded output through convolution batch normalization and ReLU layer, that is epilogue, it is passed through the decoder module where attention pooling batch normalization and linear batch normalization is used to obtain the embeddings in Titanet network for speaker embeddings. Next, coming to the function creation of how the embeddings are been obtained and how those are processed. First, we give the speaker model as the input. The manifest file which was created in the earlier stage will be given as the input and the embedding directory will be given. We provide batch size here as 1 and device as the CPU. Now we create a dictionary where we again input the manifest file and the sampling rate. We give labels as none, batch size as 1 and shuffle as false along with the time length or the duration of 20 seconds. Next, we evaluate the model dot setup and provide and apply that to the device, that is CPU, and keep the speaker model in the evaluation mode. After this, the next step is to obtain the embeddings. Here, once the test loader is been loaded with the test file, we will pick up each batch from the test loader and provide it to the embedding speaker model to create the embeddings. Here, after obtaining the embeddings, we take the shape. We take mbs dot shape 1, which means that we take the element last element of that particular array, which contains the speaker labels, and then rest of the features are then similarly appended here. After that, once we get the whole embedding vector here, next we check for the normalizing the embeddings. After normalizing the embeddings, we check whether the given label we provide each embedding with or each audio file or each speaker as with a unique name, and we check whether the unique name is then present in the embedding key or not. If it is present in the embedding key, then we say that the enrollment is already present, and if not, we say that the enrollment is not present. This is just to check whether whether it is already enrolled or not. So let us try running this both the manifest file and embedding file function. Now, once we get this enrollment and not, we create the embedding pickle file, which will be used in the later stages while creating the working for the identification purposes. So here we provide the file name and the save it in the pickle format and return the embedding file here. Next, when we define the cosine similarity to check whether the identification is done or not. So once the embeddings are mapped here, and we check it for the cosine similarity, that if it is greater than 0.7 or let us say any predefined threshold value, then it will say that the embeddings are it will say that the identification is done, and it will give the identification ID, speaker ID as well, else it will say that user not found. Here comes the most important part. After the embedding is been obtained, the output of the speakers will be a fixed length vector representing each speaker. Now, identifying task uses the speaker embeddings to train the model. However, NVIDIA NeMo toolkit uses k-means clustering method to train the speaker model, and next from the test case sample, the embeddings are provided to the trained module. So as we created the manifest file and the embedding file earlier, we create a temporary folder to give the details of the embedding and embedding files, saved embedding files, and from those paths we call the embedding files to check for the identification purposes. Here we again define highest score as 0, just to check whether the cosine similarity to check whether the cosine similarity is able to identify or not. Here, when we say that the cosine similarity is or the cosine similarities will give some particular score, and if that particular score is greater than the highest score and threshold, it will designate the speaker name with the speaker ID, highest score as the score, and actual speaker with a verification key. If highest score is equals to 0, then it would say that it could not be verified. Else it will say that identification is done. So let us try running this code. It is important to note that this NVIDIA NeMo Titanet model is trained on VoxCeleb dataset 1. So the verifying test case should be from the test samples provided by the dataset itself. So let us try running some other test case which is outside the VoxCeleb dataset. So as you can see here, the audio path is been given as the test case in the wave file format, and the enrolled embedding path is also given here. So let us run here. As you can see that this test case is not present in the VoxCeleb trained dataset or the training dataset. It throws an error which can be again handled with an exception. Now let us try with some training dataset provided by the dataset organizer. So from this I will be going to VoxCeleb task and copy this file path. Now this should identify the key and the speaker as ID equals to 10282. So let us run it again, and yes, we can see that the identification is done, and the speaker name is as said ID 10282 with a specific ID with the score of 0.78, which is greater than 0.7, and time taken is 2.58 seconds. So yes, that's all for the NVIDIA NeMo Titanet. Thank you so much.